Hi, my name is Larkin Cunningham from Cork Institute of Technology in Ireland, presenting my paper, Using Learning Analytics to Improve Digital Game-Based Learning. I'm going to cover the topic of learning analytics, how it can be applied to digital game-based learning, the types of rich data that it provides, and how taxonomies of learning can be used to design data points for storage and analysis. And I'll present an adaptive model for how gameplay data can be used to improve digital game-based learning, followed by a brief case study. Learning analytics is an emerging field of interest to educators, researchers, institutions, and governments. It's used to improve student learning outcomes, improve engagement, such as personalizing content, adapting content to the students for adaptive learning, providing immediate formative feedback, and it can improve retention by identifying early those at risk of failure or dropping out, so that you can more efficiently target intervention or learning supports at the students who need it most. Traditionally, it's been associated with learning management systems, so for example, when students log in, when they take assessments and results are posted, and other forms of engagement such as the students clicking on links for document downloads or viewing videos and so on. So there's a vast array of different types of information that learning management systems can record. And the term is also associated with educational data mining. However, there is a distinction from my perspective, which is that learning analytics requires a degree of pre-planning to identify the useful data points that you intend to store and analyze, whereas EDM is concerned more with unstructured data or vast amounts of data that weren't originally intended for analysis but can be now analysed to mine new knowledge about the way that learning takes place. So the focus of this presentation is on learning analytics and a degree of pre-planning in the data to store. In terms of its relationship to digital game-based learning, it can provide a rich set of player or learner data, and the focus in this presentation is on what data to store and how to structure it, how it can be used to improve the design and build process, how it can adapt learning in real time, how it can provide the player with immediate formative feedback, and how that data can be later used post-delivery to feed back into the next design and delivery of that particular game-based learning solution. Game-based learning has proved to be quite effective in comparison to traditional teaching methods, and a number of studies have pointed to that. And it has been shown to be particularly effective for science education if the concepts are conceptually integrated. Now, the one way to think about that is one example would be in a game teaching physics concepts. If you could imagine a player sliding along the ground, then if you wanted to integrate a physics concept, you could integrate the concept of friction. So as the player slides along the ground, the player character or avatar, you could emphasize that friction results by, for example, having smoke come up from the player's feet or flames to indicate that heat was generated from friction. So that would be one way of integrating directly into one of the key game mechanics in the game. What we are storing, of course, is data, and there are a number of perspectives that we can look at for how to determine what data to store. From a behaviorist perspective, the view would be that learning occurs because of observable events in the environment. So in a digital game-based learning environment, various events will occur because of the mechanics of the game or the dynamics of the game. And a game engine can be coded to recognize when these events occur and to trigger, for example, code that runs. We can also view learning as a progression of understanding. So, for example, taxonomies of learning, such as the Bloom's or revised Bloom's taxonomy, and Biggs's solo taxonomy, the structure of the observed learning outcome, And when we map digital game-based learning to these taxonomies, each observable progression is a potential data point to store. So as we move, taking for example Big's solo taxonomy, players will move from a pre-structural to a unistructural to a multistructural to a relational to an extended abstract level of understanding. And a game engine can be coded to trigger events when the player moves from, let's say, a unistructural level of understanding to a multistructural level of understanding. So the game could be coded such that when the player interacts with an object in the game, that could be an indicator or an observable indicator that a particular type of content or learning has been encountered. So as the player moves along a particular learning outcome, which is mapped to, for example, solo, then we can store data and context for each event that's triggered. For example, moving from multistructural to relational level of understanding. Each event that's triggered will have a context, and those contexts will include various properties such as a timestamp when it occurred, or a score that might be associated with it, for example if a little test was taken. And pace of progression can be deduced by subtracting timestamps. So we can visualize this, we can visualize the timestamp we can do some time series analysis to see the pace of progression. We can also have a look at individual mini progressions, such as from unistructural to multistructural, by subtracting the unistructural timestamp from the multistructural timestamp, for example, and that would give us the length of time it took to progress from one to the next. We can also store additional performance indicators like number of attempts. I won't dwell on this adaptive model for digital game-based learning because some of these boxes here I'm covering on the next few slides. But basically it covers all phases of the design, the analysis, design, build, delivery and post-delivery phases that are mapped to various models of instructional design, possibly using different terminology. But basically you start off by analyzing the student needs, determining the learning outcomes you need to have, and map the learning progression from a taxonomy to various data points, and map those data points to the game mechanics in the game to see what in the game will trigger those events, those progression events, implement the game mechanics to create gameplay and learning dynamics, and then have the gameplay feed into the data that's stored, and adaptive learning algorithms and can look at that data to change the gameplay to suit the player and provide formative feedback. And that data can be used to provide metrics and visualizations for retrospective post-delivery phase and summative evaluation, which feeds back into the next delivery of the game-based learning solution, but also as the game is being developed and designed to feed back into formative evaluation to iteratively improve the game prior to that first delivery of the game to a cohort of learners. So I've already mentioned formative and summative evaluation. Several instructional design models emphasize this continuous evaluation during an iterative design and build process, and also after the event, after delivery, to feed back into the next design and build phase. Models such as ADDIE and SAM emphasize this approach. So the solution can be trialed on learners and the data analyzed and visualized. And here is a very rough sketch of a sunburst visualization, which uses a heat map and breaks down learning outcomes into sub-learning outcomes or activities or items or learning objects in the game. And as players progress through them and their level of understanding builds up, so does the heat map in the visualization heat up, and the spread and the balance of learning can be viewed through such a visualization. Adaptive learning can respond to the learner context, and various algorithms can be coded in the game engine, such as when a player demonstrates lack of mastery of a topic, such as not answering a question correctly, then you can deliver new contextual learning content. We can also bring in more complex algorithms from artificial intelligence or machine learning, or we can use semantic networks to allow the exploration of related content, so that each game play experience is slightly different than the next. Data can be used to keep the player in the flow channel. This is from Csikszentmihalyi's theory of flow, to deliver content that is neither consistently too hard nor too easy for too long, to avoid the player getting bored or frustrated. And as mentioned, we can also use data to balance delivery across learning outcomes, or we can funnel players through one learning outcome at a time. Prompt feedback is a principle of effective practice. Stored data points can be analysed in real time to provide feedback to the player, such as assessment results, overall statistics, and leaderboards. We can also, similarly to the summative informative evaluation, we can also provide similar types of visualization for the player, and the player can compare themselves to other groups of players like their classmates. I'll finish with a brief case study. So I'm developing a game teaching the fundamentals of graph theory. We begin with a tutorial level that introduces the controls. Data points are mapped to the learning of the game's mechanics, like locomotion, teleporting around, connecting vertices together, and so on. And during development, I can check, for example, the duration between data points to identify mechanics that are proving difficult, and that's an example of quick summative feedback. During the main levels of the game, players complete a graph according to rules. Events with context include connecting two vertices, and the context would include the time of connection, the value of vertex 1 and the value of vertex 2. And we can give formative feedback to the player, including incorrectly connected vertices being connected by a red edge rather than a green edge. And learning in the game has been mapped to the Solo taxonomy. Future plans for the game include adaptive learning algorithms to present the player or learner with new, more unpredictable challenges, and this will avoid boredom, in other words, keep them in the flow channel. To summarize, learning analytics is an increasingly important area. It should be considered by designers through the analysis, design, build, delivery, and retrospective phases as part of a continuous improvement cycle. Learning can be seen as a progression of understanding with changes of state that can be mapped to stored data points. Gameplay data allows for rich analysis and can allow games to be adaptive to learners in real time. And ultimately, this means more engaged players, learners, and more effective learning outcomes. Thank you very much for watching and listening.